Okay, we're going to have a function that we, okay, here's a grid. We assume the spacing of the lines is 1 unit in each direction. Could be anything else, but, and let's just say we have an exponential function that does this. Okay, what is the equation of the function f of x, where this is the function f of x? You know that we can get the equation from 2 points on the line. Now, many times, I think probably, maybe even all the time, on the graphs that you see in the My Open Math assignment, you're going to be able to tell exactly what the x-coordinate is because it's going to go right through one of these grid points. Okay, and then you're going to be also able to tell what the value of f of 1 is. Now, the way I've drawn the grid, that's not the case. Remember that all we need is 2 points on the line and we can write the simultaneous equations. Okay, so let's just say we've got this point and this point. Okay, the x-intercept is always a good point and you'll see why. So let's say the x-intercept here looks like 0. It's between, the y value is between 1 and 2, a little closer to 2. So I'm going to assume this is the point 0, 1.7. And I'm going to assume that my estimate here is accurate, and this will be 1. And let's see, I'm going to say 1, 2.6. Okay, how do we get the equation? Well, the form's going to be y times ab to the x, so we're going to get 2 simultaneous equations here. So we're going to get (1.7) equals a times b to the 0 for this point, and y is 6 when x equals 1, so we're going to have 6 for y, 2.6. 2.6 equals a times 1, a times b, I'm sorry, to the 1. Okay, now this is a very convenient set of equations. Okay, this is great work if you can get it. Okay, why is this so good? Well, what's b to the 0? It's 1. So this just tells you that a times 1 equals 1.7. In other words, it gives you the value of a. A is 1.7. Now, if a is 1.7, you can plug that in here. And this is just b. You don't have to take any roots or anything. It's b to the 1 is just b. So you're going to get 1.7 times b equals 2.6. Now, that's cause for some celebration because this is, you know, the other system that we just solved isn't all that difficult, but you have to go to a calculator to do a lot of it. This one, you know, the arithmetic is very simple. Okay, so let's write it out then. So we have 1.7 equals a times b to the 0. And we have 2.6 equals a times b to the 1, which is just a times b. Okay, well, this equation tells us that 1.7 equals a. So we've got our value of a. Again, anytime we have the y-intercept, if we have an exponential function, we know that we're going to get a b to the 0, so we're going to get our value of a. without having to do any more work. Okay, now 1.7 equals A, so we take that here and plug it in for A, and that gives us 2.6 equals 1.7 times B, so B is 2.6 over 1.7. Now let's just see what that might be approximately. That's going to be 1 point, and then you've got 1.7 into 9. 1.8 would go into 9.5 times, at 0.9. And this will go in about 5% less than that, which will be about, and you can kind of ignore my mental ramblings here, but 5% less than 1.5, about 1.43. Okay, you can check my approximation here. And of course, any approximation that only has 3 significant figures, when this number goes on quite a ways before it starts repeating, it is not going to be completely accurate. But then we used estimates here that weren't completely accurate anyway. So B is, we're going to say approximately 1.43. So our model is approximately 1.7 times 1.43 to the x. Now we can test whether this is a good model or not, and it's not going to be a great one. We're going to test it to see if it predicts another point on the graph. So we test the model. So let's find y equals f of 4. And compare to what the graph tells us. Because we can estimate f of 4. We've got 1, 2, 3, 4. Our estimate is a little over what? 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe about 9.5. Okay? That's what the graph tells us. So here the point would be about 9.5. Plug 4 in for x. You get 1.7 times 1.43 raised to the 4th power. Well, 1.43 raised to the 4th power um, 1.5 raised to 4th power to the 4. I'm just going to say this is maybe about 4.2. And this would be approximately equal to 7.1. Okay? The graph predicts f of 4 equals 9.5. So here's 4. Here's 9.5, and that's how you get what the graph predicts. And let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 9.5. Okay, so it looks like one of two things. Maybe my graph doesn't really have the shape of an exponential function. And maybe I just didn't do a very good job of estimating these points. If I was off just a little bit in estimating these points, that could throw this model off a whole lot. Okay, if this is really 1.8, then that would bring this estimate up to, well, bring it up some. If this point was 2.5 instead of 2.6, that would have an influence on the number that we get here. And that could easily have influenced it. Now we could just get a feel for how precise our estimates need to be. But the point I want to make is, if we're estimating two nearby points, a little small, tiny difference, a little tall, smiting, boy, that's good, Spoonerism here. A little small, tiny discrepancy in one of these points can lead to a big discrepancy in the numbers that we get here, and could lead to a significant inaccuracy when we try to extrapolate out to larger values. So I'm going to say our conclusion here is that the result isn't great. Estimates based on a couple of nearby points are sensitive to uncertainties in those estimates. If I had used the coordinates of this point and this point as a basis for the model, it probably would have given me a good estimate for this point. Okay, and that's something you could actually test, although probably aren't going to go to the trouble unless I sign it, which I might. So, anyhow, there's how we can make estimates from a graph and obtain the value or the equation of a function given its graph.